Hello, David Snowpeck here from Snowpeck Games, and this is part 3 in a tutorial series about implementing rollback netcode in a game built with the Godot game engine. Last time, we installed the Godot Rollback Netcode add-on. We got our clients connected via Godot's high-level multiplayer API. We set up the sync manager, and we implemented the player scene using these wonderful virtual methods. In this part, we're going to make a custom MessageSerializer. But what is that? And why is that something that we need to do? Well, first we need to talk about the problem we are trying to solve. In rollback, like we discussed back in part 1, we are only sending the input, which input is usually pretty small. That sounds like it should be easy, but we generate and send new input on every single tick. So if your game simulation is running at 60 frames per second, that means you will also need to send 60 messages per second. We need all of this input to arrive eventually, or we'll desync. It's okay if input is late because we're doing prediction, but the more prediction we do, the more rollbacks will happen and the more artifacts the player will see. So the faster and more reliably we can send that input, the better experience we can give to our players. So the problem is, how can we quickly and reliably send input? Well, we are using UDP via eNet. With plain old UDP, there are no reliability guarantees. Messages can be lost, corrupted, arrive out of order. eNet has this really cool reliability layer, which is great for some things like setting up the session, sharing match configuration, like what stage are we going to play, what game mode, but it's actually kind of slow for sending input every tick. Let me explain why. Again, we're going to assume a ping of 64 milliseconds, so a latency of 32 milliseconds or 2 frames. So peer 1 via eNet sends a message to peer 2. When it arrives, peer 2 sends an acknowledgement back, which eNet will process back here on peer 1 and basically just check off that that first message was received. It got there, it's done, we don't have to worry about it anymore. And this is fine. We sent the message, it arrived 32 milliseconds later. We can't deliver the message any faster. That is the latency of our connection. But what happens if the message gets lost? So let's say peer 1 sends the message, but it gets lost somewhere along the way, which means peer 2 doesn't send this acknowledgement back. That just doesn't happen. So then eNet is going to wait some period of time, and if it hasn't gotten that acknowledgement, it's going to send the message again. And just for example purposes, we're going to say that happens after 80 milliseconds. So that means that this input from tick number 1 took 112 milliseconds to arrive, 8 frames. If that input is going to cause the game to roll back, that is 8 frames, 8 ticks of rollback, which is going to create a pretty big artifact. But we can do better because we know that we are sending a message every single frame, so we can take advantage of that fact using a technique I like to call the sliding window technique, which is super common in game netcode, not just in rollback and prediction, but in all kinds of netcode. And here is how it works. So rather than waiting some period of time to repeat messages, we simply include all unacknowledged input in every single message. And rather than sending separate acknowledgement messages, we also include all of the acknowledgements that we know the other peer hasn't received in every single message. So here's how that looks. In frame number 1, we send the input for tick number 1, good. In frame number 2, we send the input for tick number 2, but also repeat the input for tick number 1 because it hasn't been acknowledged yet. On frame number 3, we send the inputs for ticks number 3, 2, and 1, but also the acknowledgement for peer 2's input from tick number 1 because that will have arrived at this point. On frame number 4, we send the input for ticks number 4, 3, 2, and 1, as well as the acknowledgements for 2 and 1 because those are the messages that have arrived so far. And then finally, on frame number 5, we no longer need to send the input for tick number 1 because at this point, the acknowledgement for tick number 1 will finally have arrived, and so on, creating a sliding window of repeated inputs and acknowledgements. And what this means is that if a single message is lost, like let's say, for example, if the the message from frame number 3 is lost, if the next message arrives, it includes everything that peer needs to get caught up. So they only have to wait 16 milliseconds rather than the, 112 milliseconds from our previous example. So this is great, but now we are sending a whole bunch of inputs as well as acknowledgements, and we haven't talked about this yet, but state hashes for checking for state mismatches all in one message, which means these messages are actually starting to get kind of large, at least relatively speaking. This brings us to the maximum transmission unit, or MTU, which is the largest packet a router will transmit before fragmenting it into multiple packets or simply discarding it. The MTU varies from router to router, from computer to computer, but it is some value between 576 bytes and 1,472 bytes. There's a great article about this on Gaffer on Games. I highly recommend it. I highly recommend Gaffer on Games in general. There's some great articles about game netcode there. In any case, for maximum reliability, your messages need to be smaller than the MTU. The author of that Gaffer on Games article estimates that in the modern era, a safe value is somewhere around 1,200 bytes, but really, the smaller, the better, because this is the wild internet. You don't know what kind of weird routers might exist between your players. Which finally brings us to MessageSerializer. MessageSerializer is a class within the Godot Rollback Netcode add-on that turns messages into bytes. It is really great at compactly serializing acknowledgements and state hashes. It is really bad at compactly serializing your game's input. In fact, if you use the default implementation, your messages will likely exceed the MTU. And the reason for that is that the default implementation is completely generic. It needs to work for any game with any kind of input. But if you make a custom message serializer specific to your game's input, it will do much, much better, which is why pretty much all games that use the Godot Rollback Netcode add-on need to make one. Let's head over to Godot and create our custom message serializer. So the first thing we need to do is create a new script. I'm going to right-click down here, go to New Script. I'm going to call it custom message serializer.gd. Then I'm going to double-click and open that up. We're going to delete all of the code except for the extends line, but we're actually going to change that. We're going to delete where it says node, and we are going to drag over the parent class, which we can find by going to add-ons, Godot Rollback Netcode, and MessageSerializer, which you just drag over here to the end of the extends line. Now, we are going to override a single method from the parent class to start with. Let's just copy and paste that over so we can look at it. We are going to Control-click on MessageSerializer and then just copy this serialize input method. This is the default. It's simply taking the input dictionary and calling var2 bytes on it using Godot's default serialization of variant data. Let's take a look at what this data actually is and how big the default turns out to be. So I'm going to copy and paste in a little bit of code here. And all this is doing is printing out the input, changing it to bytes using the same var2 bytes, printing out the count, and then returning it. So to get our custom message serializer to actually be used, we need to go to Project, Project Settings, down to Network and Rollback. And in this classes section, we are going to click the little folder next to MessageSerializer, and we are going to double-click our custom message serializer. So let's see how that works in practice and what we get. So I'm going to start up the game and click Server over here, start up another instance down here and click Client. And once this starts up, I'm just going to move around for a little bit and then kill it. All right, if we go up into the editor output panel, we can see that some of these messages are very small. They just contain this $sign key with an integer. This is the input hash. It's used when comparing different input frames against each other. For example, comparing the real input to the predicted input to see if they are the same or if they are not, and we need to do a rollback. But when some input is actually being generated, we'll also get this key, which is the path to the node that is generating the input, and then the input dictionary that that node is actually returning from its get local input virtual method. And you can see that at its biggest, it is 104 bytes, which doesn't sound like a lot, but in the worst case scenario, we could be sending a full input buffer worth of input frames within a single message. How big is the input buffer? Well, that is configurable. If you go to Project, Project Settings, and then down to Network Rollback, the first setting at the top, max buffer size, that is the size of both the input and state buffer. The default is 20, and that means that your game can roll back a maximum of 20 ticks. This is a value that you will be tuning for your specific game. The higher the value, the bigger the buffer. That means the bigger latency your game is able to handle because it can roll back further. But there is a limit because your game needs to be performant enough to execute this many ticks within a single frame. If your game can't actually execute 20 ticks within a single frame, well, you're going to enter a death spiral and things will go terribly wrong. And so you're going to need to lower that value to match how performant your game's simulation actually is. In any case, what that means is that if the biggest input frame is around 100 bytes, and in worst case, we're going to have 20 of them, that is 2,000 bytes, which is way over the MTU. Luckily, our custom message serializer, we can get that down to something like 15 bytes. So first, let's get rid of this old code, and we are going to create a stream peer buffer to hold our bytes. We resize it to 16, which is just kind of a maximum value that we think is going to be bigger than whatever we're going to put into this buffer, just so that the buffer doesn't have to resize itself every time we write something. And then right away, let's add the return statement at the end. And here we are resizing the buffer again, but we are setting it to its actual size after we've written a bunch of stuff and returning the pool byte array. So then in the middle here is when we're going to actually write stuff to that buffer. Now, one of the first principles to writing compact data is to write required things at the beginning and to just put them in a predictable order. That way we don't need to label what the data is. We can just expect to always get that data in that order. So something we know that is going to be coming in every single input frame is this input hash. So we just write that to our buffer. It's an unsigned 32-bit integer, so we do put underscore u32. Oh, and I'm going to rename this argument to all input. We're going to be looping over the data within that dictionary in a little bit, and I wanted to use the name input for the inner data, so we call the outer data all input. All right. Next, we need to write how much input we are going to be putting here. This is a two-player game, so we're either really sending, a single player's input or no input if no input was generated, but assuming that maybe in the future we could have more players or something, I don't know, we're actually going to write a count of the items within this dictionary, and we are subtracting 1 because of the input hash. So this will write either a 0 or a 1, which can be an unsigned 8-bit integer, just taking up a single byte. Next, we are going to start looping over that input. The key is the path to the node. We are skipping over the input hash because we've already written it up here. And then, oops, I copy and pasted a little too much. We need to write this path to the message somehow. In the message, in the default, it's actually writing out this full string, but we know this can only be a certain set of values. It can either be root main server player or root main client player. So we can just turn that into an integer. So we're going to make this mapping dictionary, which we'll put up at the top, called input path mapping, which maps these individual paths to just an integer value. And then we are going to write that to our buffer. Again, this can be an unsigned 8-bit value, so just a single byte. The next principle of writing compact data is that we completely omit data that is at a default value or not present. And the way that we encode if the data is there or not is via bit flags, since we can say whether something is there or not using a single bit within some header byte or bytes. So we're going to start by making a header, which is just a integer value of 0. We're going to make some flags that are going to go into this header. In our case, the only thing we need to encode is whether or not the input has an input vector or not, so we just have a single flag. And then we need to check if that is present in our input. Here we're just getting the individual piece of input from the all input dictionary, checking if we have this vector input data, and if so, we are setting this bit on our header byte. Then we write our header, and after that, we write the actual data. So again, we have to check if the input vector is there, and if it is, we grab it, and then it is a vector, which is just 2 floats. A float is 4 bytes, so we just write, 4 bytes for the x, 4 bytes for the y, and we are done. Let's look at how many bytes that is. So 4 bytes for the input hash, 5 for the number of input, 6 for the which input path it is, 7 for the header, and then 8 for 8 more for this input vector. 7 plus 8 is 15. So we went down from 104 bytes to just 15 bytes. Now, before we can actually test this, we need to do all of the same things, but in reverse, so that the client on the other side can actually unserialize this data and use it. So to do that, we are implementing another method on MessageSerializer called unSerializeInput, which takes the serialized pool byte array that would have been generated by serializeInput and turns it back into a dictionary. Again, we are going to create a stream peer buffer. This time, we are putting the serialized data into it and then seeking back to the beginning of the buffer so that when we start reading from it, it will start at the beginning. And we are going to create an all input dictionary, which we return at the end. Now, in the middle here is when we are going to actually decode that binary data. So the first thing is we need to get that input hash, since that is the first thing that we wrote. We just do buffer get underscore U32, since it's an unsigned 32-bit integer and assigned it to the $ key. Next, we need to see how much input is going to be here, getting the input count, which was just a U8. If the input count is 0, we're done. We just return all input. Then we need to reverse this path mapping, because the next thing that we wrote, remember, was the path right here. And to do that, we make another dictionary, which is basically just that first dictionary flipped. In our init method, we actually loop over the original dictionary and create the reversed version, the input underscore path underscore mapping underscore reverse, which we use down here, grabbing the path. And then finally, we need to get the individual input, which starts by grabbing the header, that unsigned 8-bit integer, checking if the hasInputVector flag is set, and if it is, we read 2 floats, create a vector 2, and assign it to the input vector key in our input. And at the very end, we need to actually write that input to the all input dictionary before we return it, and we are done. Hopefully that makes sense. It's a lot of just looking at your serialized input and lining it up with, lining all of the puts up with gets down in your unserialized input. So let's test that, make sure we did that correctly. We'll make this one be the server, this one be the client, and when it starts, I will move around, and hey, it's moving on the other client, so we did everything correctly. There is a useful debug setting when you're trying to optimize your MessageSerializer. If you go to Project Settings, and then in Network Rollback, there is a message bytes in the debug section. This will print out an error every time a message exceeds a certain number of bytes. And this is the number of bytes including not just the input, but also the acknowledgements, the state hashes, but it does not include the extra like header information that Godot is putting on there and enet is putting on there, and the header that goes in every UDP packet. So you have to kind of keep in mind that whatever value you're targeting, the message is actually going to be a little bit bigger. So you're going to need to decide exactly like what kind of MTU value you are targeting. I'm just going to set this to 1 so that it will always print something out, and you can see what this looks like. Here, I'll set this one to the server again, this one to the client again. We will move around a little bit, kill it, and then go over here and look in the debugger, errors, and we have all these messages saying, sending message with size 77 bytes, sending message with size 60 bytes. That message serializer we just created was for our demo game, but remember we were trying to create the simplest demo that could possibly work, so there was just a single piece of input, the input vector. I think it would be good to look at a more complex example and check out the message serializer from Retro Tank Party. You'll see that it's actually quite similar to the one that we created. We're also doing a thing with input path mapping, but in this case it's a 4-player game, so it can go up to 4 different paths and then a special path when we're running in practice mode. We have a whole bunch of different inputs. So we have some more header flags. We mark which control scheme the user is using, whether it has an input vector, whether it has turret rotation, whether or not the player is shooting or using an ability. These aren't flags that denote whether data should be present or not present. These are just plain Boolean values. So rather than sending a whole byte for a Boolean value to say, is the player shooting, true or false? Is the player using an ability, true or false? We can just use a single bit within our header. So we get down here, this all looks very similar. We're getting the mapped path, which is just a single byte. We're looking at the data and filling up our header with different flags, writing the header, and then optionally writing these 2 pieces of optional data, the turret rotation and the input vector. So even though this game is quite a bit more complex and has quite a bit more things going on in its input, the message serializer is really very similar. So I think from this tutorial lesson, you should have everything that you need to create a decent custom message serializer for your game. So that's all for this part. Next time, we are going to be adding some more gameplay to our demo game and look at spawning scenes and timers in the context of Rollback Netcode. Thanks for watching. Bye-bye.